Hello everybody. In this video I'm gonna be talking about one topic which is kind of related to the data fitting more than the Matlab field diagram, but it's important for me to discuss this point in detail so that I can use it in the next video for the Matlab field diagram. So to go to the point, we need first to, I'll just go here to my Excel file where I plotted the Matlab field diagram. So we talked a lot about this diagram, but I'm more concerned about the equilibrium curve, which is this curve. We know that this curve was drawn from this equation, which is y equals alpha x divided by y minus 1 minus alpha x. And this is a simple equation that we can manipulate to get x as a function of y. So these two are the same equation, y as a function of x or x is a function of y. And we use this equation to draw everything, and we did calculations to get the exact location of each point on the curve so that we can do the calculate the number of stages, and it was kind of simple process. But in other cases we wouldn't be able to use this equation because this equation assumes that alpha is constant for all the mole fractions, and that's why the curve is symmetric, and I can use a single value of alpha, which is this. However, it is not the case for all the systems. There are other systems like this is the water methanol system. You can see that it's hard to tell from the points, but from the numbers you can tell that for x equal, this is x and this is y, and for x equals 0.1, y equals 0.01, this is 1%, this is y equals 25%. So the y is very, very large compared to x. And for the x equals 0.95, y equals 0.96, which is almost the same. So just to see it with your eyes, you can tell easily how this is different. So this is how the equilibrium curve looks like. So it's totally different from the this curve that we were talking about before, and that's why we cannot use this equation to describe this curve because it's not the same system. To do this, we need to find an equation that I can use to. I'm going back and forth. I'm sorry about that, but I need an equation to replace this equation so that I can put y as a function of x that will take that shape that we just talked about before, so we can replace this equation and do the process of calculating the number of stages. That's why it's important for me to find a way to fit this data. The first thing would come into your mind that you will go use the curve fitting tool, which is responsible for doing the curve fitting. We will just enter the values of x and y. So this is what we see here. I would add the values of x and the values of y, and I would try to find something that would or an equation that would fit well. Of course, this doesn't look like a first order polynomial, which is linear equation, so I'll go for third order polynomial. It's not good. You'd see that r squared is 85%, and the curve is not actually passing through the points. It's passing kind of between them. And this is a critical thing here actually, is that because I need to have the equation that passes almost through all the points. It cannot be just going between the points. It's not fitting, getting a best fit. It's getting an equation that describes exactly these points, because this is what I'm gonna use to calculate the number of stages. So something like this is not acceptable at all. I can try to go for higher order, but still it's not good enough. You'd see that there are some points that is higher and some points are lower. It's going like curvy way. Or a wavy way, so it's not acceptable for me to use this equation. It's gonna give me a lot of error actually in my calculations. You'd believe me, I think, if I tell you that I tried all the equations that are here and none of them worked. I also did some other trials with equations that I came up with, and I tried to fit and it didn't work. So I have to find a way actually, because it's important for me to find this equation. Otherwise, I cannot do the calculation of the number of stages, because I'm gonna be stuck at some point, which is this point. So to do this, I took a look at the curve, and I did the quick search on the internet, and I came up with a good idea actually. And this idea depends on your understanding of the curve fitting actually. The some parts of the curve would be good or you would find a good fit to some points of the curve. For instance, this part of the curve from point 3 to 1, it looks like it's a simple equation that can describe this. It can be like to a second order, third order polynomial would describe this part very nicely with a very good fit. This part would be like, yeah, you can find something that fits with this part. So the point that or the idea is to break this big set of data into smaller sets of data and to fit each one separately, so you can get an equation that, for instance, fits well with the region from point 3 to 1, and another set of data that fits well with from 0 to point 3, whatever. So if you can get this part, you can then find a way to get this as a whole equation, and this is the second part of it. So the first part, which is an important part actually, is to find where you are going to break this set of data. So you can say I will break it from here into two parts. This part would be fit, I'll get a good fit for this part separately and one for this part separately. I already did that. It gave a good fit actually for this. It was very good fit for the region from point 3 to 1, but this part didn't give a good fit. I tried to change the range from point 3 to point 2 and it didn't help much. So I thought of breaking it into three parts actually. So, and this is what gave some good results to me, which is getting an equation from 0 to 0.05 and from 0.05 to 0.3 and then from 0.3 to 1. So let's go ahead and try that. But before we do that, I need to go here and break this into x1, y and y1. So I have the set of data which is x and y. This is x and this is y. And I'm gonna take from 0, 0.1, 0.01, 0.02, and 0.05. So this part of the data would be the x and x1 and y1. I'm gonna make x2 starting from 4. So I got an important point is to make sure that the point between two parts must be included in the fitting of both, so that the curve would end up to be like a smooth curve. So this is gonna be from 0.05 is 4 to 0.3. So I have 4, 5, 6, 7, 8. So it's gonna be from 4 to 8, and this is y2 from 4 to 8, and then x3 is gonna be from 8 to 16 or 16, yeah, and this is gonna be from 8 to 16. So now I have x1, x2, and x3 are together will make the whole x, and this is what I'm gonna use for the first fitting, and this is for the second, and this is for the third. So now I'm gonna go back to the fitting tool. I'm gonna go for x1 against y1, and you can I'm gonna use third order polynomial. You see the r squared equals 1. So the curve is exactly going through each single point of the 4 points. So it's a great fit actually for this part. You can add one more fitting here. Oops, I'm gonna call it, make it between x2 and y2. Again, you can try different equations, but I found that the third order polynomial is good. So it tells me that y2 is 9 by 1 and x2 is 5 by 1. So I think I did something wrong about x2 and y2. I think they are good. I don't know why. I did a big mistake. I make this as x3 and y2. I didn't change this into y3. So now it should work well. So I make it y2, and you see it's not a very like that perfect, but it's 99.8% goodness of fit. So it's good enough actually. Um, Still, this difference is a very small difference. For me, this is acceptable, at least for this application. So I have now this, and the third part would be x3 against oops against y3, again third order polynomial, and again you can choose to try any other equation. You can make logarithmic, whatever kind of equation that you feel it's gonna be a good fit. And this is a very good fit, is 0.9992. So now I have three equations that describe the system well. So I'm gonna make this in Matlab go side by side. I'm gonna now open an M file so that I can put everything together. The first thing I would put data, which is here, just to have everything in the same file, and I don't need to worry about information that got missing. And then I'm gonna get x, yep, so this here. So now I have the experimental data. I can put this as experimental data. So I have all the experimental data here, and now I'm gonna get the fitting data. So I have three equations now, so I'm gonna call them y1, y2, and y3. y1 is a function of x, y2 also is a function of x, y3 is a function of x, and this function is what I got from here. So for the first part, it's gonna be 2817 multiplied by x to the power of 3 minus 489.5 multiplied by x to the power of 2 plus 29.91 multiplied by x. And actually this part, the constant is 10 power minus 17, so it's almost 0. I'm not gonna put it. For the second part, it's gonna be 42.25 multiplied by x to the power of 3 minus 27.52 multiplied by x to the power of 2 plus 5.912 multiplied by x plus 0.3929. So actually this is the worst part of it, is that you're gonna write a lot of equations, but this takes only a few minutes and it's done once, so you don't need to worry about this anymore. 153 multiplied by x to the power of 3 minus 1.90 multiplied by x to the power of 2 plus 0.6552 multiplied by x to the power of 1, so I'm not gonna put the power, plus 0.7173. Okay, so now I have the three equations, and the so I'm gonna so now the point the last point that I want to do is to write an equation that will calculate y from x from this equation for the region of x from 0 to 0.05, and then go to this equation for the value of x from 0.05 to 0.3, and then the third equation from 0.3 to 1. And this is the tricky part. What you would think is that I would use an if conditional, but unfortunately this you can write an if conditional, of course, but this is not always applicable, and sometimes you need a function handle that you'd use to do everything, so you wouldn't have the luxury to put an if conditional for all the cases. And for the function handle, to the best of my knowledge, I don't know that it's possible to put an if conditional inside this function handle thing. So what I came up with is to use something that will do what an if conditional would do without writing an if conditional, which is using the relational statement. So I would make y equilibrium, I would call it like this. It's gonna be a function of x, and I would write the code, and I think you'd understand when I write it. I would say that x smaller than or greater than or equal 0, and x smaller than or equal to 0.05, and then multiply this by y1 of x. So what you would see here is that when you look at this part, if x is greater than or equal to 0 and smaller than or equal to 0.05, this bracket would be equal to 1, which means that y1 would be calculated because it's multiplied by 1. But if x is greater than 0.05, then this bracket would be 0, and then this will not be calculated because it's multiplied by 0. Whatever the value, then it wouldn't matter. So it's like I'm putting an if conditional, but I'm not actually writing an if conditional. And I'm gonna do that for the second part, so that I'm gonna say that x is greater than 0.05 and x smaller than or equal 0.3 multiply by y2 of x, and the same thing for the last part is gonna be x greater than 0.3 and x smaller than or equal to 1, then it's gonna be y3 of x. So it's now done. So what you would think is that, or if you look at the code now, then I don't need this anymore now, or now I don't need it. So when you look at the code, then you have each one of them is which I got from the fitting data fitting tool, and then this equation would pick which one to calculate from according to the value of x, which is kind of close to what I do for if conditioning. Um, um, you need to make sure that the x is smaller than or equal 0.05, then you wouldn't put equal here. So it would be included in one of these two equations, y1 or y2 or y3, whatever, but you cannot include this in all of them. So just to make sure that it's fine, I would just plot both on the same graph. So I'm gonna plot this as just I mean markers only. I'm sorry, I just forgot the name. And I'm just adding one thing. And then I would hold the plot and then fplot y equation from 0 to 1, and we'll make it black. So what I'm expecting now before I run the file is that I would have two plots, one for the experimental data and one for the fitted data, and I'm kind of confident that this data that or the function plot would be passing through all the points on the curve. And this is exactly what I found here. It is impressive actually to see that the curve is passing through all the points with a function handle. Of course, you would find sometimes that there is kind of the points where the curve is meeting from the first part meeting the second part. It might not be very smooth, and at this part you can simply try to include the common point in the other equation. So I would remove it from here and point make it here again, make it, remove it from here and make it here. So I'm just moving the common point from one equation to the other. Let's just and now I'm running the file. Oops. I think I have an issue here. It is in column 55, line 14, column 55. Oh, I'm sorry. Now it should work. So if you see this part was kind of fixed, but this didn't is not fixed that much. You still can play around with it. You can find another equation that fits well, or you can do some add one more power, like make it fourth order instead of third order. Whatever the solution that you might think of, but just think about what you now have and what you we're trying to get with fitting with one equation for all the data. This is way more better now, and the curve is exactly passing through all, or almost passing through all the points, if not exactly passing by all of them. And again, if this doesn't work, you can break it into 4 parts, 5 parts, 6 parts, whatever the number of parts that you want to break the curve into, but you would get the curve going well through all of them. One last thing that we need to kind of check is that the equation, or this curve, passes through 0 and 1. So the curve must pass by point 0, 0 and 1, 1. So if you want to take a close look at the curve at the 0 part, so I'm gonna go from 0 to 0.01, 0.01. You'd see that the curve, this is the equilibrium and this is the operating, or the fitted data. This is the 45-degree line. It's already passing through this point. Let's go to the other part at from point 95 to 1, and from point 95 to 1. You'd see that it's not going exactly at this point. So the fitted data is going or intersecting the 45-degree line here, and it is kind of shifted by, it's a very small value actually. It's not a big deal, but this is not acceptable for distillation exactly, especially, I mean, because in some cases you need to get a very high purity, let's say 99.8%. Or 99.5% like this. So if your point is here, the XD, then you will not be able to start the calculation of the number of stages, because you would have the operating line above the equilibrium curve, which is a disaster actually. So you need to shift this curve up a little bit. So it's not a big deal actually if you try to use the equation to get y equilibrium at 1, it's gonna be 99.78. So you need to just increase the equation by 0.0022. So what I'm gonna do here is to go increase this by 22. It's gonna be 95, and now you can do the plot. It wouldn't seem different here, but when you go for axis and take a closer look, it exactly going to this point. So it's solved, and again, it's not that big deal. If you look at the equation here, it is passing through all the points as we did before. It's not gonna change anything. I hope this helps. I think it's going to be useful for many applications actually, just for the distillation, but I'm going to use this equation in the next video, so I hope you understand how this equation comes from, so I can use it easily next time. So I'll see you then, and goodbye.